I know it's tempting to use as many mics as you can when recording a drum kit, but before you do that, watch this video, because by the end, my hope is that you understand why sometimes less is more. And if you still decide to use multiple mics, I'll share a few tips with you that will help you to avoid the common problems that come up when using multiple mics. Thanks to SoundRadix for sponsoring this video and supporting audio education. They have an amazing plugin called Auto Align 2 that addresses some of the problems I'm about to share with you, and you can use the link below the video for a 14-day free trial. But first, we need to understand the problems that a plugin like this solves. Let's say we have a drum kit that we're trying to record. If we decide to just put one overhead mic above the drum kit, we'll only be capturing the sound at a single point in space. But if we add in a second overhead mic, we're now recording at 2 points in space. You might initially think that the left microphone will capture the elements on the left side of the drum kit and the right microphone will capture the elements on the right side. But drums are loud, and at this distance, both mics are going to pick up every component of the drum kit. The benefit of this is that we will now have a wider stereo image of the drums. Rather than just one mid microphone panned down the center, we can pan the left overhead mic to the left and the right overhead mic to the right. The elements on the left side of the kit are slightly closer to the left microphone and will therefore be slightly louder in the left mic and slightly quieter on the right mic. And the same thing happens on the right side. It's kind of like a pan knob. If I pan my voice to the left, what actually happens is that my voice becomes louder in your left speaker compared to your right speaker. We accomplish a similar effect when using two mics, which brings stereo dimension to the sound, where if you close your eyes, you can actually point to where the different elements of the drum kit are in space. But the elements closest to the left overhead mic aren't just louder in the left mic, they also reach the left mic before reaching the right mic. And that adds to the stereo dimensionality thanks to the Haas effect, where we localize sounds to some degree based on which ear hears it first. But it also potentially poses a problem. Right here, I've got a speaker and two microphones. They're currently the same distance from the speaker, which means the sound from the speaker reaches both microphones simultaneously. But listen to what happens when I change the relative distance to the speaker. Depending on this difference in distance, frequencies with particular wavelengths will be summed together and others will be canceled out. What we're hearing is the effect of phase interference caused by a time of arrival difference. When mics are the same distance from the speaker, all of the frequencies will be in phase. But when we shift one of the mics back in time, some wavelengths will be perfectly aligned, some will be perfectly misaligned, and others will be somewhat aligned. When you look at the result on a graph, it looks like a comb. Thus, this phenomenon is often referred to as comb filtering. Getting back to our drum example, the same thing could potentially happen to the sound of any particular drum or cymbal in the drum kit. Let's take the snare drum, for example. If the sound from the snare takes a shorter path to the left mic, it will be louder and earlier in the left mic, which not only results in the snare sounding like it's coming from the left side, but also applies a comb filter to the tone of the snare when we mix the two mics together and play back the recording. Because of this, recording engineers will often measure the distance from the snare to each overhead mic and ensure that each overhead mic is equally spaced from the snare. This will ensure that the snare will be the same level in each mic and that the snare will be in phase in each mic. But thanks to the nature of space and time, the two mics simply cannot be the same distance from every component of the kit. And that's okay. That's what makes it stereo. And that's what gives the recording dimension. However, it's common to use multiple mics when miking a drum kit for reasons other than enhancing the stereo image. For example, even if we like the overall sound of the drum kit captured by the overheads, we may choose to use an additional spot microphone on the snare drum so that we can increase the level and shape the tone of the snare independent from the other components of the kit. And when we mix the snare mic with the overhead mics, we're mixing two moments in time. The close mic captures the snare drum sound almost immediately after the snare drum is hit, but the overheads will capture it slightly later because the sound has to travel through space to reach the overhead mics. Depending on the wavelength of the fundamental frequency of the snare, this distance may or may not result in phase alignment at that frequency at the overheads. If the snare mic and the overhead mics happen to be out of phase at that particular frequency, we will not only hear a loss of punch in the transient, but we could also potentially hear a thinning out of the snare because the close mic might be positive while the overhead mic is negative, meaning they work against one another and cancel out. You can quickly check this by playing the snare mic and the overhead mics together and experimenting by inverting the polarity of the snare mic and listening to the tone of the snare. If you get a good sound with one of them, either regular polarity or inverted polarity, that's great, and you can roll with that. However, it may be worth it to actually delay the snare mic in time so that you're not just finding the point where that frequency is more in phase, but where it's actually in phase. This is a feature of auto align. We just add the auto align plugin to the overhead mics and the snare mic, and it will analyze the three signals and find the best possible alignment for us. The same thing can be done for the kick drum mic, the tom mics, and any other mics you might have on the drum kit. Anytime I add the plugin to a channel, it shows up here in the side panel and automatically groups instruments together. There are several techniques that auto align uses to accomplish the best possible phase alignment between all of the instruments in the group. If the problem can be solved with a simple polarity inversion, it'll do that. If the problem requires a time delay, it will do that as well. This is the equivalent to sliding the region in your DAW timeline. But this isn't a complete solution, and that's why auto align takes it a step further. To keep it simple, let's imagine we only have a mono overhead that's pointed down toward the kit, and we also have some tom mics, snare mics, and kick drum mics. All of these close mics could be simply delayed in time, but that doesn't address the problem of phase shift at particular frequencies. This is important to understand, the difference between polarity, time of arrival, and phase shift. Flipping or inverting the polarity of an audio signal simply inverts the waveform. Positives become negatives and negatives become positives. And this impacts all frequencies equally, regardless of wavelength. Time of arrival differences will have different impacts on different frequencies. The same time delay applied to two different frequencies could result in different phase relationships. A 1 millisecond delay could put one frequency completely out of phase while putting another in phase at a slight delay. This is why we get comb filtering, like I mentioned before. However, microphones don't necessarily respond with linear phase at all frequencies in all directions. In most cases, there will be some phase shift. A microphone may have a mostly linear response to most frequencies that interact with the mic on axis, while it may create some phase shift at particular frequencies when off axis. This is why auto align, in addition to polarity and time delays, also implements its proprietary spectral phase optimization, which is what you see going on here with these multicolored meters. Now, the developers at Sound Radix are a lot smarter than me, so there might be some other stuff going on here, but one way they do this is by using all-pass filters. An all-pass filter is like an EQ, a high-pass filter, or a low-pass filter in that they all use phase shift. The difference is that an all-pass filter doesn't have the same impact on the frequency balance of a signal that you'd expect from an EQ. This means you can apply a phase shift at a particular frequency in a very transparent way. In fact, the all-pass filters within auto align could be useful when you EQ or high-pass microphones during the recording process to counteract the impacts of those phase shifts when the signal is mixed with other microphones. The green on these meters indicate where there is no phase shift applied. The red indicates frequencies that have 180 degrees of phase shift, and the other colors indicate some phase shift between 0 and 180 degrees. The plugin listens to the audio and automatically determines the best configuration. And I suppose this could theoretically be done without auto-align by using a bunch of all-pass filters, polarity switches, and time delays. But that sounds pretty complicated when auto-align does that automatically when you press the align button. Another common technique is to use multiple mics on a single drum. The most common example is to do this with the snare drum, miking the top and the bottom. Again, these mics are at different points in space, so the sound will potentially reach them at different times, and each mic will have its own unique phase response. But there's another issue with this technique in particular. Think about what happens when a drummer whacks the snare drum. The batter head moves downward when it's struck by the drumstick. Then pressure builds inside the drum, causing the resonant head to move downward as well. And after that, they both continue to oscillate at various frequencies. But when you think about it, even though both heads initially move downward, the batter head initially moves inward while the resonant head moves outward. From the perspective of the top mic, the batter head is moving away from it, and from the perspective of the bottom mic, the resonant head is moving toward it. And this could result in a nearly equal but opposite signal in each mic. If you're starting to understand what I'm talking about in this video, you'll see that this could result in severe cancellation. Now, it isn't always that simple. Different mics respond to different frequencies differently, as I've already mentioned. So you'll want to check using the same technique as before. Listen to the top mic and the bottom mic with the polarity switch in the default position, and then listen to the two mics with one of the polarity switches inverted. Of course, this is something that auto-align listens for as well. In addition to the time changes and phase shifts, the plugin will invert the polarity if necessary for the best possible phase alignment. It's also common to use two mics on the kick drum. In this case, the mics usually face the same direction. Sometimes they don't, but they're often in different acoustical environments, and they're almost always a different distance from the drum heads. In live sound, your tools are usually very limited, but if there is a delay handy, I've often seen engineers add delay to the internal kick mic to push it back in time so it's in phase with the external mic. It can be kind of tricky to hear when mics are in phase. It's much easier to hear when they're out of phase. For this reason, it's helpful to first invert the polarity of one mic, then add delay until the two mics almost totally cancel, and finally remove the polarity inversion, putting the mics back in phase with each other. Again, in the studio, we have a lot more tools and time to experiment. And one such tool is auto-align, and it's by far the fastest to use and the most automated that I've tried. Another helpful tool to know about is a Lissajous meter, sometimes called a vector scope. The basic principle here is that there is a dot that will move throughout the graph, leaving a line behind it that traces its path. The shapes left by that trace give us insight into the relationship between the two signals. Let's run some test signals through this meter to understand what it's telling us. If I send a low-level 1 Hz signal through the left channel only, we'll see a relatively short diagonal line leaning to the left. Increasing the input level will make the line longer. Decreasing the input level will make the line shorter. Alternatively, we can turn on the auto gain to automatically increase the input gain over the course of a few seconds to fully utilize the graph. Running a signal through only the right channel will draw a diagonal path that leans to the right. Now, I'll duplicate this test signal, sending one copy to the left and one copy to the right, but for now, they're equal in level, which creates a vertical line. Notice that the correlation meter reads +1 when the signal to each channel is in phase. If I flip the polarity on one channel, the left and right channel will now be in opposite polarity, the trace will become horizontal, and the correlation meter will read -1. In general, we want to see a squiggle that's mostly vertical. If the squiggle is horizontal, it indicates that there's a large difference between the two signals. And if it's vertical, or somewhat vertical, the two signals are mostly the same. This is currently set up for comparing the left and right channel for monitoring the coherence in a stereo setup, but these meters can be used to compare the phase coherence between any two signals. For example, we can look at the demo from earlier with the 2 mics and a speaker, but this time I'll play a sine tone so that the path is simpler. The line starts out vertical, and at this frequency, it becomes horizontal at about this distance. But when we change the frequency of the sine wave, that distance will change. And this is such an important point to understand, which is why I keep reiterating it to you. The art of recording sound sources in the real world is rarely simple or perfect. There are so many variables that could cause phase interference, such as multiple mics, reflections off of walls, phase response of microphones, etc. And even if you know the different distances, a given delay will only solve the problem for some frequencies, because the wavelength of each frequency is different. That's why it's useful to use tools like auto-align, Lisa's meters, and of course, your ears. You can download a free 14-day trial of auto-align with the link in the show notes below the video. And in the next video, we're taking a closer look at comb filtering. I'll see you there.